Yeah, so good morning to all of you. So this is going to be the second part of our course, wherein we are going to, focus and look at what happens, why we need a feedback in transducers. So you have studied the concepts of requirement of feedback and in your control systems course, right? You have looked at feedback mathematically. And here also we are going to look at it, with the mathematics along with, its application in actual, sensors or transducers. So let's proceed. One second. So what we are going to discuss is the importance of feedback. Then we'll discuss anemometer, which is nothing but a flow sensor. We are also going to look at feedback, the utility of feedback in inertial sensors. And then we are going to look at flapper nozzle amplifier, which is nothing but a pneumatic or a pressure sensor. And based on all these like four different concepts, we will try to establish why feedback is essential and what is the impact. I mean, from the mathematics that you have seen in control systems, we are going to study, how it is going to impact actual systems in real life. Okay, so let's get started with a very simple example. So herein, what I have tried to do is actual sensor or a actuator or a sensor. We have just assumed it as a simple low-pass transfer function, and I'm calling it. I'm taking a generic name, meaning it can be thought of as an actuator or a sensor. Not to say that there is any particular device I have in mind in this case, but by some electrical equivalent, I just want to set the ball rolling about the effects of feedback, right? Because we are most comfortable in dealing with electrical networks, and that will kind of set the ball rolling for us and it will let us know what we can expect as we study the transducers in the next few classes. So, of course, we have an actuator or a sensor. That means if we have an actuator, what we will need is an electrical signal, and if we have a sensor, what we will need is a mechanical signal, right? So in both cases, what I am assuming, I'm modeling the electrical or the mechanical, input or the signal in two components. One you can see is a DC component, and the other I am modeling as an AC component, right? So why a DC component is needed? Because in many applications, you will see in the subsequent classes also, for example, even in pneumatic sensors, right? You will see that it is important to have a bias condition or an operating point of the transducer well defined, so that the system works in the highest quote unquote performance bracket, right? Meaning this bias condition or the this voltage is going to maintain the right operating condition for the sensor or the actuator, so that the performance, we need a certain, good kind of behavior, right? For example, linearity is one thing, right? That we need. Gain can be another, right? So we would like to operate the actuator or the sensor at a certain operating condition, and based on that requirement, what we do. Oops, I don't know. Yeah, so sorry, I'm operating from the guest house, and yeah, some noise is coming. So yeah, so based on the we would need to use either an electrical bias condition or a mechanical bias condition. So the requirement of this is clear, right? For example, let's say I have an amplifier with this kind of a characteristics, let's say, right? V out by V in, right? If I need the right amplification characteristics, I mean, if I want, so this is the DC characteristics, right? And if I want to use such a block or a module as an amplifier, what I will try to do is try to bias the amplifier, let's say at an operating point, maybe somewhere here, because that's where we see the gain is maximum, right? The V out by V in, the gain, which is nothing but del V out by del V in, right? So this is maximum, right? But to bias the module at this point, we need some biasing condition, right? So this is achieved by having the operating point voltage shown here like this, right? Okay. And then this small signal Vs, this is the signal that we are going to amplify, or this is what we need to kind of deal with. It can be for an actuator, it can be an electrical signal, or for a sensor, it can be a mechanical signal. And typically, this signal, this particular signal Vs, if you think from a pure magnitude point of view, will be much lesser than VOP, the operating point, because this will ensure that the operating point does not kind of change, meaning the input signal does not change the operating point of the system, right? So that's the key thing that we want to ensure if we want to kind of make this whole transducer work as a small signal. I mean, if we want to make it work as an amplifier, we need to ensure that the characteristics of the amplifier or the sensor is kind of maintained without disturbing the operating point itself. So this Vs should be the input signal, which will be much smaller in magnitude than the biasing voltage or the condition that we are applying to ensure that this whole actuator or transducer works in the right operating point. So this should be clear, right? Now, if we simplistically look at the, output voltage by input voltage, if we look at the transfer characteristics, this is pretty simple, and which you people have done it. It's nothing but it's a low pass, very simple low pass characteristics, and we can write it as V out by Vs. Please note the operating point. This voltage does not appear in the transfer function, because this I have shown, as I said, just to ensure that the actuator or the sensor is at the right operating point. Once that is done, we can, for our small signal analysis, we can short this voltage, right? We can short this voltage and assume that we are applying only the signal source Vs, and in response we are getting an output voltage V0, right? So V0 by Vs is 1 by 1 plus tau s, right? So obvious things that we can see is the bandwidth is limited by the transducer itself, right? So Rs and Cs. So the transducer itself limits the bandwidth, and also the output impedance. If the transducer will need to actually pass the output signal to some readout circuit, right? So the output impedance of such an arrangement will be limited, right? So now let's move on and see if we use the whole system. If we have a feedback, can we get rid of these limitations, the bandwidth limitation or the output impedance limitation? Can we get rid of these two limitations or not? So what I have done, I have taken a voltage amplifier, an ideal voltage amplifier, right, which will amplify an input signal, input voltage V with a gain of A, and I have taken a feedback also with a feedback factor beta. And here I have an arrangement wherein the input signal source, be it electrical or mechanical, is added in a negative feedback configuration, right? So please note that I'm trying to just build a generic kind of diagram it can be, you can think of this as either a real electrical network, or you can think of it as a actual mechanical. Just hold on, let me see if I can stop the noise. Just hold on, please. Yeah, so yeah, today is a tough day, looks like, after the mid-semester, quite a few distractions. First, Microsoft Teams played trolls with me, and now the workers in the guest house there. I've asked them to stop. Let's see. So yeah, so please understand that, you know, this feedback, I'm just trying to make a generic circuit to set the ball rolling. It can be the actual, transducer, or it can be, it can be, I mean, it can be, this simplified model is valid for an actual, I mean, for, it can be shown that, you know, the same principles will hold true even if it's an actuator or a sensor, right? So let's see if we come up with this kind of a scheme, what happens. So then if we look at the transfer function, this I have not derived, this I think you people should be able to derive, not a big deal, right? So the voltage here, so this is V0, so the voltage here will be Vs minus beta times V0, right? And this will be V0 by A, right? So Vs minus beta times V0 and V0 by A, this we know, right? This is nothing but the input and the output of this low pass filter. So by relating these two quantities with this time constant, you should be able to derive the transfer function. And if we rearrange, we can show that the V0 by Vs, so this is the DC component, becomes A divided by A beta plus 1, and the time constant, we come up with a new time constant, tau prime, and this tau prime is nothing but the tau that we saw here divided by the loop gain. So what that means is the bandwidth. This was a single pole system that we have taken, right? So the bandwidth is directly related to tau here. So if we see here, now that we have reduced the tau, so if A is large, so let's say A is 1000, right? And if beta you can assume to be 1 for simplicity, right? So we can see that the new time constant becomes much smaller than the original time constant that we had, right? But then nothing comes for free, right? What are the problems? What are the problems do you think we have created in trying to increase the bandwidth of the system? In life, also, just like in life, we don't get anything for free, right? So what are the problems we have created for ourselves here?
The gain is reducing for the same
Yes.
frequency.
Correct. Gain is reducing, but there is a little bit more to it. So if you see what is the gain here, right? So as Ayush is saying that the gain is reducing, but then let's take the realistic numbers, right? An amplifier with a gain of 1000 is pretty realistic. A 60 dB kind of gain is a very simple amplifier, right? Not a very costly amplifier. And beta equal to 1. So we are left with 1000 divided by 1001, which will be approximately equal to what, 0.999 something, right? Almost 1. So there is a little bit reduction in gain. Here the DC gain was absolutely 1. So there is a little bit reduction in gain, right? But not much. Of course, another thing is now that we are driving the output voltage with an ideal amplifier, we should be able to drive a realistic load, RL, right? Which will, without loading the actual transducer system, without loading the actual sensor system, should be able to drive an output load, right? And as Ayush mentioned, so we have landed up ourselves with a gain error, slight gain error, and somebody can say that, look, we can get rid of the gain error or make it negligible by making the loop gain, A beta factor, this A beta, if we make it higher and higher, right? Then actually beta in this case is 1. So if A beta becomes higher and higher, you will see this will become approximately equal to 1 by beta, right? So we can actually set, so we have actually a gain error, all right, but also we have now a control over the actual closed loop gain that we want from the system, right? So if beta is 1, then it is fine. But if beta is, let's say, 0.5, we can actually have a gain out of the system of 2 or whatever, right? But there is an error from the intended gain versus, so this beta we are using to set our gain, but then because of the finite loop gain, there will be a slight error that we will make. But typically that is not a big concern for us. In most of the situations, you will see that is not a big concern for us. What, however, is a big concern is this amplifier itself will have its own poles, right? So even though here I'm assuming this amplifier as an ideal amplifier, in reality it is going to be not a real amplifier. This will have its own poles, and that will make the system more complex. We have one pole coming from here itself, the transducer itself, and then we will have other poles coming from the feedback loop, which means we need to now take extra care, or we need to analyze the system to ensure that the system is stable, right? Any questions up to this point? So this math should be clear to you, right? I just took a very simple example to drive home the fact that what happens because of feedback. It's a very simple, and we will now go on and see actual real examples. And of course, because we are using an amplifier and with all this feedback and all, the design complexity increases. This amplifier also will take its own power, and you have to buy this amplifier from the market. So you will have to spend more. In addition to the actuator and the sensor, you need to buy the amplifier, or you need to design the amplifier yourself, which will increase the system cost, right? Okay. So now, yes, Saurabh, you want to say something?
Yes, sir. Sir, like, what do you mean by improved drive strength? Is it like we can control the gain? That's right.
Yes, that you can actually. That's a good point. I mean, I should have probably added that being able to control the gain, right? When you control over gain, it's actually an advantage, right?
Yes, yes.
Yes, we can. I should add that actually. Yes, correct. This is actually an advantage. But then we need to be careful of one thing. So let me ask you. So this is a good point actually. So someone says, so I took a very nice example of beta equal to 1 or beta equal to 0.5 or whatever, right? So some, one of you become very greedy and say that, sir, why don't we have a large gain in the closed loop itself? So why can't I set beta to be, let's say, 0.001? Will that be a problem?
But then, sir, like the bandwidth, like won't be,
Yes.
like won't improve.
Bandwidth is one thing. Bandwidth is definitely one thing. So here somebody can say that, look, I need not, improve the tau by 1,000 times or whatever, right? But so basically, let's take realistic numbers, right? So let's say A is 10,000, which is 80 dB, right? And beta, let's say, is 0.01, 100, right? So A beta, if you look at A beta, we are still at 100, right? A beta is still 100. So someone can say I'm, which is a significant number, right? And I have a closed loop gain of 1 by beta, which is equal to 100, right? So basically my bandwidth also has improved significantly and my closed loop gain is also big. What do you think will happen? Meaning, is that a problem? Do you think are you going to land up in problem, or is that okay? I mean, mathematically it looks okay, but realistically, do you think we can do it? So realistically, having a very high closed loop gain becomes a real challenge. Because you will see if we have a, so basically if you see now A beta instead of 1000 or 10,000, right? Now my A beta itself is 100, which is fine in the sense that my gain error is still acceptable. But what problem you will end up with a real amplifier system if you have a high closed loop gain, right? You will find that making the system stable becomes extremely challenging. And hence, when you end up designing instrumentation amplifiers, right? So for example, I mean, in general purpose amplifiers, when you are actually doing analog circuits, right? The general purpose amplifiers will, let's say, have a overall, let's say, open loop gain of around 1,000 or 10,000, anywhere between 60 to 80 dB. And then the beta will be maximum, maybe the beta will ensure that the closed loop gain is maximum 2 or maybe 2.53. We typically don't go higher than that. So that in itself is used, I mean, for normal general purpose applications, that is what we use. But when you look at instrumentation amplifiers, right, the configuration itself becomes quite different, right? And instrumentation amplifiers, designing one instrumentation amplifier with a high gain, that itself is a very challenging task. So the point is, there will be, we cannot unilaterally set the beta value and become greedy and say that, okay, I have achieved a high gain, because you will see there will be, so all the parasitic poles that are going to come here, right, are going to create problems once if we try to increase the closed loop gain significantly, if we try to make it significantly large. We can make it, but then the design becomes extremely challenging, right? So we'll, and we can discuss the real amplifier designs. So that in itself is a very interesting discussion. Unfortunately, we'll not be spending that much time on designing amplifiers in this course, but this will give you an idea of wherein, the kind of system challenges you will land up with if you were to, make an electronic system around an actuator or a sensor, right? So let's proceed for now. So we are first going to look at anemometer, which is nothing but a sensor used to measure flow rates of fluids and non-conducting liquids in open channels and closed pipes. So this is important because if the liquid itself becomes conducting, right, then the physics of the sensors becomes very complicated. Meaning the simple equations, heat transfer equations we are going to look at subsequently will, the equations will become much more involved because the liquid itself is conducting, and it will become pretty involved. We are not going to look at those kind of examples. Anemometers are not used for the kind of anemometers we are going to discuss. We are going to focus on non-conducting liquids, okay, and gases in closed pipes. So this is how an anemometer kind of looks like, typically made of tungsten wire with a thin platinum coating on the surface. So you can see that these, if you look at the dimension of the sensor wire, it's extremely thin, and we have large gold-plated steel supports and why are these large? We'll talk about this later. And in fact, we're going to look at modern anemometer systems also. For now, this is how it looks like, and this is my sensor wire. Okay. So simplistically, what we do is we can have a current I flowing through the wire, right? This is a thin wire sensor, and so this resistance is what we are interested in. We need to ensure that the supporting wire or the supporting conducting metal that we have, that resistance is negligible compared to the resistance of the sensor wire. And please note that the velocity is flowing normal. It is flowing normal to the wire. I mean, the way we hold the sensor is such that the velocity is normal to the wire, which ensures the heat transfer between the wire and the velocity, and the fluid, that is at its maximum when you hold it in the knob. So that actually gives you a good sensitivity of the overall system. So if we look at the heat transfer equation, right, and in steady state, what we will see is the heat that is generated in this wire is given by I square RW. RW, I'm using the this W suffix to denote that it's a sensor wire. You can think of it as tungsten also. If you think, that the wire is made of tungsten material, so the heat generated is given is this. I think we all understand, and this will be equal to the heat that is actually being dissipated in the fluid. And so here are the, again, this derivation of this is beyond the scope of the subject, but we can all understand what will be the heat that will be dissipated. Area, which is the surface area of the filament that is exposed, the amount of area that is exposed to the liquid. This is the area. TF is the temperature of the fluid. TW, temperature of the fluid, is known to us. Please understand that we are interested in measuring the flow. We are not interested in measuring the temperature. In a complicated overall system, we might actually end up measuring the temperature of the fluid as well. But as of now, we'll keep things simple. We will assume that the temperature of the fluid is known to us. It is not varying. The temperature of the wire, so if you look at it, right, in this equation, we can maintain few things as constant, right? We can either say that the current that is going to flow, we can make the current constant, or we can say that the temperature of the wire, this we can make constant. I repeat, if you look at the equation, velocity of the fluid that is flowing, that is not under our control, right? Because this is what we are measuring, right? The temperature of the fluid is known to us. We know that, okay, the fluid is actually being used in a certain system. So that this is, for now, this is not a variable, right? Area of the wire known to us, not a problem. J, this is nothing but a Joule's mechanical equivalent of heat. So some physics constant, right? Known to us. This small a and small b, this depend on sensor dimension and fluid properties around the sensor. So these actually are, like, we can derive this. If we actually work out the physics, the a and b can be derived. Probably I might have a more detailed expression for a and b, but we are not going to derive a and b for ourselves here in this course. So what all things are under our control? The current that we have, that we are forcing through the wire, that is under our control, or the temperature of the wire. These two things are under our control. And based on these two controllable parameters, anemometers are of two types. One is constant current and the other is a constant temperature. And we are going to discuss both types of anemometers, and we are going to derive the transfer function, and we are going to look at how, the transfer function, how the feedback principles actually come into picture for both types of transfer functions. Any questions up to this point? This is clear, right? See, any equation that we look at, right, guys? In fact, even in the first portion of the course, I keep saying we have to understand it is not about mugging up the equation. Because see, when you are going to actually work in the industry, right, all this information will be available to you, right? And also in the tests that I conduct, right, or in the question papers, right, you will see that I don't expect you to remember big equations. I might expect you to remember, okay, whether it is proportional or inversely proportional. To that extent, you should remember the equations. But what I do expect all of you to understand is when we write an equation, right, what are the dependent variables, right, and what are the independent variables? Independent variables is what I will have control on, right? So I, in this case, is an independent variable. I can control I, right? Or TW, the temperature in the sensor. This is a dependent variable. If I want, I can control the temperature of the sensor material, right? TF is not in my control. Area, of course, we know, right? And RW, please understand, RW is going to be a function of the temperature itself. So all what my expectation is that as design engineers, right, you should be able to understand what parameters you can control and what you cannot. Because based on that, the equations that I mean we will be dealing with to design the overall system, we will try to control the independent variables that we have in our hand, right? And actually the relationship between the independent and dependent, that we need to know. And based on that, we can design the system, right? So as I mentioned, we have this current in our control or temperature of the sensor material in control. So we can have two types of anemometers, a constant current anemometer or a constant temperature anemometer, where the sensor wire resistance is held constant. And this kind of makes sense because the resistance itself, typically the resistance of this thing will be of the order, I mean, this is how it will look like, right? Alpha T. Actually, you can say T minus T naught, right? So depending on the temperature, the resistance of a metal wire will keep changing, right? So if we hold the temperature constant, then what we are ensuring is the resistance of the sensor wire is not changing. Okay. So constant current anemometer. Actually, today let us have a little bit shorter class because what has happened is I can tell you also why I want to break off now, because you can see some of these things have been messed up because I had to restart the computer. The variables, Microsoft PPT has a problem. Every time I open the document, this suffix and this thing gets messed up. So because Teams today was typically what I do is before the class I will ensure all the variables are looking proper, but because today I had to restart, this has got messed up. So today I would say let's stop. It's a shorter class today. We didn't discuss much. We started 5-10 minutes late, and then there was disturbance in the middle, but we'll make up for it. So let's start tomorrow. Let's start the discussion on constant current anemometer. Right? So we'll stop for today. Thank you.